fine. Okay, so today's lecture, so I will be giving 3 lectures, today 2 and 1 on Monday. So today's lectures would be more basic than what you have been encountering so far. So that also means that you have to be more interactive. I will ask you of the answers, I will just wait until you give me the answer, because some of them you might have seen, some of them you might not, but you can work it out from what you have. So these 2 lectures I will be covering the basics of theory of angular momentum, and then on Monday we will do some more advanced stuff on Kramer's degeneracy and Landau levels. Okay, so we will start. Let us see what we can do. We will start with finite rotations. Okay, and we will show that just by some pretty pictures that they do not really commute. Let us say I have a block like this, something like this, wooden block or something, and this, let us say this is the my z axis. So we will do rotations in the anti-clockwise direction. This will be Rz, rotation around z axis. Similarly, this will be our, let us say, y axis, and this will be our x axis. So this will be rotation around y and rotation around x. So let us do a rotation around the z axis by 90 degrees. Right? So Rz by 90 degrees. Okay. So what we will get is something like this. Okay, this shaded area has moved on that side. And then we will rotate about the y axis by 90 degrees. So my shaded area now has moved on the top. Right, like this. Okay, let me repeat the operation in a different order. Let me rotate the y first. Right. So what we have now, the block here, right? We have rotated the y axis by 90 degrees around the y axis. So I get like this. Then I rotate around the z axis by 90 degrees. Yeah. We started with this, rotated around z by 90 degrees, and then rotated around y by 90 degrees. This is what we got. We started with the same stage. We first rotated around y, we got this, and then rotated around z, we got this. These two are suddenly different, right? You had the shaded areas on top, you had the shaded area on the right. So the way to represent this is that Rz and Ry, if you have this order, is not the same as if you had Ry and Rz. Okay. So let us make this more concrete. Okay. So if my rotated coordinates are xy prime, yy prime and zy prime, and I can write this as some operator, let us say rk, on the original coordinates. Okay. So, what do you think would be the form of this r operators? Let us say rz. What would be the form of rz? You have to tell me that. Yeah. How do you derive it? Is very simple. You have this coordinate. For example, I will give you a hint. You have this coordinate. Okay, and you have a vector a. And let us say I am just thinking about 2D, because if you move around rz, the z coordinate will remain the same. So, it is treating it 2D with the. So, I can always put this as 1, the z as 1, and then it is not going to mix x and y. So, we will put the 0. But what about x and y? Let us say it used to be x and y at the beginning with the angle, let us say phi, and then I move by angle theta, right. Of course, the vector length remains the same, does not change the length of the vector, and this vector coordinate now is x y y prime, x prime y prime, right. So, how are these related? Right. So, x prime equal to x cos theta minus y sin theta, right. Similarly, y prime you can find out, it would be x sin theta plus y cos theta. Yeah, you have seen this before with finite rotations. Okay, so we will put that here. So, cos theta minus sin theta and sin theta cos theta. Okay, and z prime remains the same. Okay, now we have to derive the forms of r y and r x. Okay, r y and r x. So, let us call r y first. Can you work it out for me? I will wait few minutes and try to work it out. So, the simple rule how to do it is that you cyclically change the coordinates. You go, let us say you have x, y and z, you go to x to y, y to z and z to x, and see what you get. So, initially we have, let me write it here, x prime equal to x cos theta minus y sin theta, y prime equal to x sin theta plus y cos theta, and z prime equal to z, right. That were the transformations that we wrote in the matrix form. Okay. What you do, you switch x to y, y to z and z to x, on the right hand side and on the left hand side. See what you get. That would be our one of the rotation matrices. Before doing this transformation, can anyone tell me on the top of the head what transformation would be? Will it be Rx or Ry? If I do this cyclic change, and when you say the answer, you have to say why. That is true. So, that would be Rx, right? That is the simple way of thinking, that look at the one that did not change first. Z did not change, now we were changing it to X. So, this has to be Rx. Okay. So, I put the easier ones. which one is this, y prime or z prime? Y prime is y prime, I think you are confusing with z prime. Z prime would be y sin theta plus z cos theta. That's what you got. That might be z prime. Okay, and y prime is y cos theta minus z sin theta. Okay, just work it out. We come to that. Okay, so that means we have cos theta minus sin theta and sin theta cos theta. Okay. So we have Rz, Rx, and we need Ry. This we know would be y because it's y. The other ones you have to tell me. Yeah. Now you start from here and then do the cyclic rotation, or you can do here also 2 cyclic permutations, or from here you do another cyclic permutation to give you this Ry. Anyone yet? What would be the, sorry, let me write it. What would be my Ry? Cos theta 0 sin theta. Right. Great. Okay. So everyone should get this. Now, have you written this down? Because I'll erase and go to the next thing. Yeah? Okay. Okay. So, I mean, just from the picture we showed that the finite rotation won't commute, right. So, here if you do the multiplication and go ahead and substitute and figure out what the matrix products are, you will find that Rx Ry is not equal to Ry Rx. Right. Now, let us do something else. Let us say that theta is very small, okay, and we will expand sin theta and cos theta, and I will find the last stage where it stops to commute. So, let me explain how. So, let us figure out Rx theta is very small, okay, and then figure out Ry Rx for the same thing, and then take the difference so that we can calculate this commutator. So, the first attempt will throw out any terms that is greater than theta. So, theta square and beyond will throw out, right. Only take terms up to theta by doing a Taylor series expansion of cos theta and sin theta. Okay. So, cos theta, what is the Taylor series expansion? When theta is very, very small, right. So, 1, first approximation would be 1. Cos theta, sorry, sin theta, theta. Okay. Let us replace sin theta by theta, cos theta by 1, see what you get. So, maybe some of the guys who are sitting at the back can come at the front, otherwise I will start asking from the back. Samne, it's all empty, please. Don't worry, don't have to be afraid. Problem is clear, right? You have the expressions, you replace cos theta by 1, sin theta by theta, and then take a 2 matrix multiplications. One you have to multiply in this order, the other one you have to multiply in this order, and then take the difference. Anyone yet? What do you get? Rx Ry minus, yes.
0 minus theta square minus 0,
But
0,
theta square you have to ignore, right? Anything beyond theta you have to ignore. So if you do that, what you get? So you have the 0, right? So if you take terms up to theta, neglect everything beyond that, then it commutes, right? So infinitesimal, very, 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 very small theta, it's like it's not moving at all. It commutes. Let's go do a little bit more rigorous. We got a term above. So we'll neglect everything. So neglect everything above theta square. Okay. So here now you have to take another term, not only one. And of course the sin theta term will not change because the other term is theta cube. So theta cube we ignore, but here you have to also take theta square, 1 minus theta square by 2. And then do the same exercise and then ignore any term above theta square. See what you get. This one, you calculate everything above theta square. Theta square you keep, but anything above you neglect. Theta cube, all those terms you neglect. Sorry. Yes. So this matrix that you should get is minus theta square 0. So 0 minus theta square 0 and theta square 0 0 0 0 0. Please check whether you are getting this. So, your in the initial matrix here, for example, the terms you are going to keep is 1 minus theta square by 2 minus theta, theta 1 minus theta square by 2. Similarly, for ry, same. And then take multiplication, you get theta. Of course, you have theta square here, that means you will also get theta to the power 4, right? You get theta to the power cube, those terms you neglect. Only terms you keep are up to theta square. So, if you do that, I mean, there might be algebraic mistakes that you have to take care of, but if you do that correctly, you should get this matrix 0 minus theta square 0 theta square 0 0 0 0 0. Okay, write it out. You should get that. Okay, so let me write it in a slightly different way. We'll write it as Rz theta square minus identity. Right? The identity operator is any of these rotation operators or any with 0 angle. Yeah. So, let me write it here clearly more. So, we computed this commutator, and what you get is 0 minus theta square 0 theta square 0 0 0 0 0, and we can write it as Rz. In theta I will replace with theta square, right. So, Rz theta square minus Rne 0. Any rotation you rotate by 0 degrees, that means you do not rotate at all, right. That is an identity operator. Okay. Are you clear on this? What was the Rz operator? Rz operator was so we started with theta, right. We said that let us start with theta, neglect everything above theta, and if you did that, then we saw that it commutes. Okay, that is our first result. Then we said that okay, let us go another higher order, see if we find a non-commutating property or not. Yes, but very small is my choice. What is very small? Yes. Okay. Yes, but at what extent? Small can be anything. Yeah, of course, everything is less than 1, but how less? Right, that is the question. If it is very small, then we go up to theta. If it is slightly higher, we go up to theta square. If it is slightly higher, we go up to theta cube, and so on and so forth. Exactly. So, at theta, it computes, right. So, that is exactly the question we are trying to answer. We try with theta, that is the smallest approximation, linear approximation that we can do. But if you do that, then it commutes. And we know that at finite theta, it does not commute, that we have seen. So, then we ask the question, what happens if we increase the order by 1? So, instead of theta, we go to theta square, right, and there we see that it does not commute anymore. Yes, it does not commute. So, that is why we will get the commutation relation for the operators. If we make it very small, then it is not generalizable to the higher orders, okay, because that is a special case we saw. Finite does not commute, very small it commutes, right. So, we need a point where it starts not to commute, so that we can extend it for finite rotations, and that would be our fundamental relation of angular momentum operators. We will come to that in a second. Yeah. Okay. So, are you clear on this? Because we have Rz was, what was Rz? Rz was 1 minus theta 0, theta 1 minus theta square by 2, 0 1, right. That was Rz if you take up to theta square. Okay. Now what I am saying is that we will replace theta with theta square, which means that this term is gone now. This becomes theta square, this becomes theta square, right, because if I replace this with theta square, this becomes theta to the power 4. So we neglect that, right. Now this matrix is equal to this is the matrix we got, right, the commutation relation. What is the relation between these two matrices? This matrix minus the identity is this matrix, right, because it does not have the diagonal anymore. So this commutation relation is basically Rz theta square minus the identity. Clear? Any questions? Okay. Okay. Now we want to use these relations to derive the fundamental commutation relations of quantum mechanical angular momentum operators. Okay. Now then we have to ask the question that what generates rotation. For example, what generates translation? Translation is generated by linear momentum. Okay. Time evolution, for example, is generated by Hamiltonian. Similarly, rotation is generated by angular momentum. Okay. So if you have that, then we can write an operator which is known as the evolution operator, infinitesimal evolution operator. This is written as identity operator because identity operator makes sure that if nothing happens, right, if the angle is 0, time is 0, distance is 0, you keep at the same position. Okay. So that is one minus I, G and epsilon. What are these? G is some Hermitian operator and epsilon is some finite, very small quantity that you are looking into. So if it is translation, then it is distance. If it is time evolution, right, then it is time, and if it is rotation, then it is angle. Okay. So that means our infinitesimal rotation operator in some direction d phi angle is written as 1 minus I. J is our angular momentum operator that we will be using, but it requires a direction. Okay. That is why this direction notation. So for example, Jx should be J dot I, right. Jy would be J dot J, small j, if I, J, K are the basis vectors in x, y, z direction, right. So this is J dot n and H bar is to make sure that units are correct, and you have angle d phi. So that is the rotation operator for infinitesimal rotation. If the rotation is very small, that would generate rotation, okay, from angular momentum. Okay. So what are we going to do now? What about the finite rotation in the z direction, right? We take the z direction and finite rotation. What would be, how do you get finite rotations from here? So the way we are going to get finite rotations, we will rotate infinite times the infinitesimal rotations, right? 1 rotation, 2 rotation, 3 rotation, 4 rotation, 5 rotation, infinite of them, right? So basically you take the limit n tends to infinity 1 minus I gz by h bar phi over n, where phi is your finite angle. I am dividing the finite angle into n parts, and I am allowing the n to go to infinity, meaning that I am going to recover this finite angle by doing very small rotations, to the power n. Do you know why? What is this limit? Exponential. Sorry. Okay. So this is e minus I gz phi by h bar. That is our finite rotations, right? You have seen this is the exponential operator as your evolution operator, same as in time, right? You talk about quantum dynamics, you talk about evolution and time is e to the power minus I h bar t, I h t if you take the h bar out. That is because you can write the infinitesimal evolution in time like this, you do it infinite times. You take this limit and then where does this to the power n comes from? Why is to the power n? Anyone? N successive rotations, right? So each rotations, remember that when you are doing one operator after another, it products, right? So you do one rotation, you do second rotation, it's a product. The cumulative effect is the product. Third rotation, another product. Fourth rotation, another product. Infinite rotation, infinite products. So you take the limit, and the limit comes out to be the exponential operator. Okay. Now comes your part. We will do the same trick as above, as before. So we will do this dx some theta, dy some theta, minus dy theta dx theta, and again we will neglect everything above theta square. So how do you do it? You have the exponential operator, you expand up to theta square. You do this expansion of the exponential up to theta square and do this multiplication in this order, okay, and tell me how do you get. But you have to be a little bit careful not to, so when you get something like this, so this will be a function of jx, right, and this would be jy. So if you get terms like this, these are not going to be equal to jy jx. So don't switch order when you are doing this multiplication. Okay? Okay. So try doing it and tell me how do you get. There will be lot of cancellations here and there, so do it carefully. to theta square. Huh? Jx jy you do not have to take, just keep it as Jx jy. You will get a form, you do not get an answer, but you get a function of Jx jy. You just use this expression. So, for example, dz theta is equal to 1 e to the power minus I jz theta by h bar, right. Huh? So, I expand it. What would be my expansion? What would be the second term? Next term, what would be the next term? Theta square and then this square. So, minus jz square theta square by h bar square, right. So, if I expand this, you should get this, right. It is an e to the power x 1 plus x square plus Taylor series expansion x square by 2 factorial. Okay. So, there will be 2. You are familiar with this, right? Taylor series expansion of exponential. Yeah. Okay. So, you do the Taylor series expansion of this exponential, you get this, plug it in here. Now, plug the corresponding x and y there and figure out what you get. Anyone? No, it will not be 0. What you should get is minus jx jy minus jy jx theta square by h bar square. That is something you should get. Go through the algebra, this is important. Simple algebra, yeah. So, what we are trying to do is clear, right. We have this, we are trying to get this commutator, and we know that each one for finite rotations are these exponentials, and what we want to do is to keep up to theta square term, expand this term and then figure out what the commutator is. Yeah. If anyone has problem understanding, please ask. But at the end of the day, you have to do the algebra. Okay, so let me write it in slightly different form. Okay, so this Jx Jy minus Jy Jx is the commutator of Jx and Jy. Yeah, and what was our result from the finite rotations? Our result was that if we keep up to theta square, then commutator of Rx Ry, we could write it as Rz theta square minus the identity. Yeah. So here we are going to, this is our left hand side, right? All we did was to replace this rotation, finite rotation operator with the quantum mechanical rotation operator. Yeah. So that was our left hand side. So what is our right hand side? Right hand side we have to keep up to theta, right? Because we are replacing theta with theta square. If we use any other term, that term we have to neglect. Okay. So this was our dz. So 1 minus I jz by h bar theta. Okay. So this is 1 minus I. This is our right hand side. Jz. We have replaced theta by theta square, right? Divided by h bar minus 1, because we are that was our 1. So this is equal to I jz theta square by h bar. So we will equal left hand side equal to right hand side. Okay, that was our result here. We get minus jx jy theta square by h bar square equal to minus I jz theta square by h bar. So the theta square cancels out and we get jx y is equal to I h bar jz. That is the relation you possibly have seen million times. Yeah, that's how you derive it. Okay, so we'll move on. So that is and then there is a slight complication. What happens when you exchange x, y and z? So per operator. So if you do that, we can do a more general form of j I j z is I h bar I j k j k, that takes care of the sign. So if I have j y j x instead of j x j y, then it would be minus. That symbol takes care of the thing that you have to maintain certain order. In that I j k order, if you have a reverse order, there will be an introduction of sign. That is known as a Levi-Civita symbol. Yeah. Okay, that is our fundamental relation of angular momentum. Now we'll move ahead and do something. What can we do? Let's see. We'll derive another important relation, the eigenvalues. So this is clear, right? Before we move forward, anyone has any questions about this? See, the algebra part you should try, right? In physics and to chemistry also, who are at least in the computational or theoretical chemistry, they should not shy away from doing algebra. You can do mistake, you should do mistakes, right? That's where you learn from. But if you are afraid of doing the math, then you are not learning. Okay, so try it for sure, do mistakes and figure out where the mistakes are. Okay, so we'll by the way, I have nothing against experiments. I mean, they are very great also, right? And you should know about these things irrespective of theory or experiments. Yeah. Okay, so we'll move on to eigenvalues and eigenvectors of the angular momentum. So I'll write. I'll start by writing the answer that we all know. We will try to derive that answer. Yeah. So if we have a square operator acting on some k represented by j and m. Why we represent by j and m? We will come to that. What is j square operator? We will also come to that. Right. That operator is written as j into j plus 1 h bar square jm, and if you have jz operating on jm is equal to mz h bar jm. Right. So you have two operators, j square, jz, the eigenvalues are j into j plus 1 or m, right, and we will try to derive these relations. Okay. That is our final answer, what we are seeking. Okay. So j square operator is j dot j, right. So you have operators, for example, you see sometimes p square operator or p to the power n operator. That is just those operator operated n times. Okay. So you have j square means j dot j. So j, each of them you can write as jxi plus jy j, right. So this you can write as jxi plus jy j plus jzk in 3D, right, and take the dot product of the same thing, right. So this will come out to be square plus j square plus jz square. Okay. Now this is your homework you should do. I am not doing it in class. That you should show that j square commutes with any of the j's. Okay. You take this operator, try this commutation, and again jx square is jx jx, jy square is jy jy, and then you have to manipulate, do some algebraic manipulation to write it in terms of other commutators, and you find out that this is true. Should try to work it out. Okay. Now what do we know about commuting operator? What does it mean if you have commuting operators? Anyone? We have a simultaneous set of eigenvectors, right? Nice. So now we have to make a choice, because you see that if I take j square, fine, but if I take jx for example, I cannot take jz as a commuting operator, because jz will commute with j square but not with jx. So you have to make a choice, right. By convention, the set of operators that are taken are j square and jz. There is nothing special about jz. It is just by convention we take the z axis, right. So we will build our eigenvector out of j square and jz, and we will say that the eigenvalues related to jz is m and eigenvalues related to j square are j. What are those will come in later, and so we designate our eigenstates using the eigenvalues. That is why we write j and m, right, just a notation, nothing else. Okay. Now since we have, I will do one small change. Since we know already the eigenvalues of these things and they are slightly different from j and m, we will for now call them as a and b. Okay. We will come to what those eigenvalues are, and everyone will represent these eigensets with j and m, but for now let us call them a corresponding to the eigenvalue of j squared, b eigenvalue of jz. Okay. Okay. Now in order to derive all these relations, we need a second operator, second set of operators. These are known as ladder operators, and many of you have encountered this. So the ladder operators are defined as, again this choice is solely based on the fact that we have taken Jz out of the picture. Jz and J square, we know that we are forming a set using these commuting operators. So, we will manipulate the Jx and Jy to define a second set of operators. Why they are required, why that algebraic structure is required, we will see in a moment, but that will be our definition for our case, the ladder operators. Okay. Now, one thing is also clear, that if we define like this, then J minus is actually the dagger of the J plus, right, because Jx, Jy, their Hermitian operator, J dagger would be Jx dagger would be Jx, Jy dagger would be Jy, and since they are, it will sign. Okay. Now, let us figure out some commutation relations. What about commutation of J plus minus 0, right, because J square commutes with both Jx and Jy, we do not have to work it out, we will know that since commutes with both and it is a linear combination of those two, it should be 0. Okay. So, that is 0. What about J plus J minus? What do you think it would be? Of course, this will you have to work out, but anyways, okay. Okay, so there might be some factors, but you should realize that see Jx, J plus is made up of Jx, Jy, right. J minus is also made of Jx, Jy. So, this should be at least proportional to Jz, because the commutations that you will get are of Jx and Jy, that will eventually give you Jz, right. But of course, the factors you cannot figure out without doing the algebra itself, but it should be proportional to Jz, right, that it should be clear to you. Okay. Okay. And what else? What about Jz, J plus minus? What is that commutation? That is again if I have to take a guess, right, of course, the factors, right, that will come when you do the actual algebra, right. So, if I have to take a guess, see this is composed of xy, Jz is eventually the commutator of Jx, Jy, right. So, my guess would be this would be something proportional to J plus minus, because this would be commutator of Jxy related to this would be Jx, Jy. So, eventually you have again commutators of Jx, Jy. So, my guess would be J plus minus, but you have to work out the math, and this comes out to be plus minus H bar J plus minus. Okay. So, we have all the commutators. These are part of your homework, that you work out all the details of these commutators, that you should get this. Why we are taking this commutator? No, this one. Oh, as I said, there is no reason to choose Jz in as such. You could have taken any one of them. You could have taken Jx, Jy or Jz, but once you take it, you have to keep that set, and you have to develop the algebra based on that choice. So, for example, if I had taken Jx here, right, then these ladder operators would have been made of Jy and Jz, so on and so forth. So, you have to take care of that, but by convention anything, the first choice is the z axis, you align along the z axis everything, and you take that as a convention. There is nothing special about the z axis as such. Okay. Oh, sorry, I should not have. Let me keep this part only, and then I will keep erasing this part, other parts. Okay. So, we created some operators that we defined as Jx plus minus I Jy, right. We want to see what is its effect, right. Does it change A or does it change B, right. Okay. So, let us start with A. Let us ask the question, does it change the eigenvalues of J square? Okay. So, how do you do it? J square we know, if it J square operates on this, we get some function of A, right, because that is the eigenvalue. Okay. What we are going to do, we will operate J square on this ket. See, this is an operator operating on a ket. I do not know what is the result, right, but I know that it will be another ket, right. Operator operating on a ket, you should get a ket. What that ket is, I do not know. Yeah. But let us try to figure out whether we can derive some equation using this equation. Yeah. Okay. But we also know that J square commutes with J plus minus. Okay. So, we switch the order. Commuting means ki this operator times this minus the other order. So, if it is 0, that means it is J square times J plus minus is equal to J plus minus times J square, right. So, this is equal to J plus minus J square AB. Yeah, we switch the order because they commute. Okay. So, this is equal to J plus minus, and J square operating on AB should give you AB, right, because A we told that is the eigenvalue of J square, right. So, this is equal to J plus minus AB. What does it tell you? It tells you that J plus minus, whatever its effect is, it has no effect on A, right. Whatever state you get, the A notation remains the same, because you know that if you had started with AB, J square operating on AB, the eigenvalue you have got is A. You operated with another operator, you get the same eigenvalue, meaning that whatever J plus minus effect is, it is not changing A, right. Okay. So, what about B? Does it change B? Let us look, figure it out. So, we do the same trick. Can you work this out? So, again the trick is the same. Remember, this commutator is not 0 anymore. So, you have to use the commutation relation and flip the order. Why do you want to flip the order? Because I know what is the effect of Jz on this. I do not know what is the effect of J plus minus on AB. That is what we are trying to figure out. But if you flip the order, then I know how to operate that. So, use the commutation relation to write something where you can put Jz in front of AB. So, this is Jz, J plus minus plus J plus minus Jz. Yeah, this was our commutation, which is Jz J plus minus J plus minus Jz. We have just replaced that with this one with this. Okay. Okay. But this we already know. This commutation we already know. So, this is J plus minus AB plus you have J plus minus B AB. Yeah, because Jz operating on AB gives B AB. AB is an eigenvector of Jz. Remember, we had a simultaneous set of eigenvectors which we called as AB, right. B was the eigenvalue of Jz, A was the eigenvalue of J square. A we already saw, J plus minus has no effect on A. Yeah. Now, so Jz operating on AB will give you B times AB. Yeah. and this one we know that this commutator is plus minus h bar j plus minus. So this is equal to b plus minus h bar j plus minus ab. Okay. So you have an eigen operator operating on some ket, you get the ket back, right, with a different eigenvalue. So the effect of j plus minus is actually to change b by units of h bar. Am I clear on this? The effect of j plus minus. So previously we figured out if we use j square, it has no effect. Yeah, we got the same eigenvalue. Now we generated another ket, j plus minus has operator AB, and use this jz operator on that ket. Right? We get an eigenvalue that is less than or greater than by h bar. Right? So what j plus minus is doing, it's either increasing or decreasing in the spectrum of B by units of h bar. Right? That is the reason why it is called a ladder operator, as if you are going up the ladder or coming down the ladder. Okay. So we can write that j plus minus on AB is equal to some constant and AB plus minus h bar. Okay. Now, given these relations, see there are two important things when you do work out all these details. One is that you should try to work out all the details, and the second, you should not forget what is the key important component of that derivation. Okay. So we will do the derivations, but at the end we will keep reminding us where it comes from, what is the origin. Okay. So given all these commutation relations, can we figure out, is there any limit of B? You are going up the ladder, where does the ladder go? Does it go to heaven or it stop somewhere? And you come down, where does it go down? Right? Is there a limit? Given that you have an eigenvalue j square. Let us try to figure that out. We will go through the derivation again. So we will try to work out this operator j square minus j square. Of course, j square is jx square plus jy square plus jz square. So j square minus jz square is equal to jx square plus jy square. Right? What can we write it as? We can write it as j plus j minus plus j minus j plus, half of that. Yeah. You just work it out, j plus is jx plus ijy and j minus is jx minus iy. You take the product, right, square product, and you will see that it is plus minus half of this. So now we also know that this is equal to j minus is actually the dagger of j plus. Yeah, because one is jx plus ijy, you take the dagger, you just change the sign, because the jx and jy are Hermitian operators. Yeah. So this is equal to j plus dagger plus j plus dagger j plus. Okay. Which means that if I take the operator that has to be greater than equal to 0. Can we take that? C dagger C. If C is an complex number, C dagger C is not a complex number, right? Mod C square, right? So, we have these operators, we are taking the product of dagger and itself. So, whatever we do, if we squeeze into some ket, what this ket is immaterial, whatever that ket is, that expectation value that we get should be greater than 0. Yeah. Okay. Now, what is this? What is this eigenvalue in expectation value? What is this expectation value? Can you figure out? We know j square operating on this. You know jz square operating on this, right? So, this is a minus b square. Okay. And then we assume that AB are normalized and so on and so forth. So, j square operating on AB would be AB would be 1 and you will left with A. Jz square operating on this would be B square and then this, that is just a number comes out. So, A minus B whole square greater than 0, right, which implies that A is greater than or equal to B square. That puts a limit on B. Yeah, you keep on going down the ladder or keep on going up the ladder, you will hit A or minus A. That is what it tells you. Yeah. Okay. Now, let us start with this state B max, right. That will be a state. You have some B, you keep on operating ladder operators, at some point you hit a maximum, right. Now, if I operate with j plus on that, what should we get? What do you think we should get? Exactly. So, you should get 0. There is no state beyond that, right. So, anything working with 0 would also be 0. So, this A B max equal to 0 and then you can write, if you work out the math, you will show that this can be written as j square minus jz square minus h bar jz. See, in the algebra of angular momentum, you see there are lot of manipulations you have to do. You have to do a lot of algebra, but at the end of the day, you should not forget what you are trying to do, right. At the end of the day, everything will try to convert into either j square or jz, because that is the operators that we know what happens when it operates on this kind of kets. So, everything do this algebraic manipulation, whatever we write, we should convert it to this form. Okay. So, if it operates on B max, then we get the relation A equal to B max D max plus H bar. Okay. Because I know now all the operator what happens when it operates on this, and if it is equal to 0, that means the eigenvalue has to be equal to 0, right. The case cannot be 0, that then it does not make any sense. Yeah. So, if you operate on this, you will get this A minus B max square minus H B max, and then we just rearrange this. Okay. Okay. Let us play the same game with B min, right. We start with B min and operate with J minus, we will get 0. Then we operate with J plus J minus A B min, okay, and work out the algebra form, exactly same form, but similar form, and then we will get A equal to B min minus H bar. Exact same logic. You cannot go beyond minus. So, if I try to go minus below B minus, I should get 0. Similarly, I cannot cross B max. If I want to cross B max, then it should be 0, right. With that, we get these relations. So, we have to equate these relations, right. In one case, both are logically correct. We got to these results from different ways, right. In one case, we started with J plus, the other case with J minus, but both of them are relations with something with A. So, they have to be the same, right, which means that B mean times B mean minus H bar equal to B max into B max plus H bar. Okay. What are our choices? Can you tell me if this relation has to hold? What are the choices you have got? What are the choices will make sure that their relation is correct or the relation holds? For everything, if you just plug in some number, this will not hold, right. There must be some relation between max and min for which this will hold, right. Say I take B mean is equal to B max plus H bar, right. Replace B max plus H bar, because all I am doing is equating this and that. That will hold, but that does not make any sense, right. How can the minimum be greater than the maximum? That does not correct. The another option I have got is B max equal to minus B min, right. Plug that in, minus B max minus base minus minus plus, so B max plus H bar, right. That would make sense, right. So, we are saying that we can go up, you hit a maximum, you go down, hit a maximum, hit a minimum in such a way that the maximum is equal to minus the minimum. That is the only way all these logically correct. Okay. So, basically I can take B to be some integer. Now, why integer? Okay, let me think about something, that I have some quantity that goes from an integer or some value minus a to some value plus a, okay. And then I do it in integer of something, that was integer of H bar, right. What are my possibilities? Can you tell me? Let us start with 3/4, right. If I 3/4 take a minus, then I go to minus 1/4, right. Minus 1/4 minus 1 could be minus 5/4. I do not hit minus 3/4, right. What about 1? If I start with 1, minus 1 is 0 and then minus 1. So, integers will work, any real will not work, right. For any real, these relations will not work where you go by H bar or some unit. The only case it will work is integers and half integers. I can start with half, minus 1 would give me minus half, I stop there. So, if you have this relation that we start with some number and decrease by unit 1 and hit minus of that number, the only possibilities are integer and half integers. Okay. This possibly you have learned several times, that these j values can be either integers or half integers. Ultimately, we got a very fantastic result, but what is we did all this algebra, right? But beyond that algebra, if you think of it, what is it consequence of? It is the consequence of the fact that we started with certain kind of commutation relation. That was the key, right? With that commutation relation, the only thing that we could get is that the j values have to be either integers or half integers. Okay? And then we had a relation between A and B with B max and B mean. You can plug that in, and the eigenvalue of j square would come out to be j into j plus 1 h bar square. If you take the eigenvalue to be of B to be m h bar, then you can plug the maximum B max or B mean, and you will get this relation. So we have come to this relation that j square and jz, if you take the eigenvalue of jz mz h bar, then the other one has to be j into j plus 1 h bar square. Yeah, and j values can only be integer or half integer. Okay. Okay, I think we are almost up. So we'll stop here for the first lecture. We'll take a break and come back and talk about eigenvalues of j plus minus that we have not done yet. Yeah, eigenvalues of j plus minus, orbital angular momentum, and addition of angular momentum. So I think Mustansir was covering this L plus S spin orbit coupling, right? That is a consequence of you have to know how to add angular momentums. Okay, so we'll do we'll see what are the good quantum numbers. You have multiple angular momentums, either orbital or spin, and what would be the good quantum numbers, and based on that we will see that there are two set of quantum numbers which are commuting among themselves, and any commuting operators you can generate as simultaneous eigenvectors, right. So those two spaces are connected, and we will derive some not general relations, but we figure out how to connect those two subspaces. Those coefficients that connect them are known as Klebs-Gordon coefficients, and we will talk about that in the next lecture. Okay. Okay.